Hello, everyone. Thanks so much for joining me. Today, I'm going to talk about a recent feature in the Spark 2.3 release called Pandas UDF, aka Vectorized UDF. So my name is Li Jing. I'm a software engineer at 2 Sigma Investment. 2 Sigma is very much a data science company. And at 2 Sigma, there are a lot of data scientists that are trying to build sophisticated machine learning models to forecast the financial market. Starting about 2 years ago, we started to build the next generation data analytics and machine learning platform at 2 Sigma to deal with the large amounts of data that we're seeing these days. Throughout the process, I got very interested and also impressed by 2 kind of independent systems. On the one side, there is, of course, Apache Spark, which is extremely powerful at the time and still today in deal with large amounts of data. On the other hand, there is Python. As we all know, it has been increasingly popular over the past few years. And my fellow data scientists, they started to use it and really started to love it. And when I look at it myself, I'm also impressed by its powerfulness in deal with all kinds of issues in data science. However, at the time, there has been a problem that has been bothering me, which is it seems to be overly complicated trying to integrate these 2 systems. They doesn't really work with each other very well. And I remember when at the time I was talking to Wes McKinney, who is the creator of Pandas, about this problem. And he introduced me to this pretty exciting technology called Apache Arrow. I'm sure all of you also have heard the mention of Apache Arrow in Reno's keynote about hydrogen today as a way to communicate data between SQL system and machine learning system. And that is where the journey started, and I'm very excited to share with you today. Here's going to be an outline of the talk. First, I'm going to give a quick overview of data science in Spark and in Python and Spark today. Then I'm going to introduce this new feature, Pandas UDF, in the Spark 2.3 release. And finally, I want to finish the talk with some ongoing work, which I'm very excited about as well. So here is the classical workflow for predictive modeling. Predictive modeling is just this common problem in data science where you want to build a model on existing data and you want to predict the model, or you want to predict future data using this model. And this is the workflow we've seen many, many times in many occasions. When we look at why Python is so great about dealing with this kind of workflow in data science is because Python ecosystem has so many libraries to deal with each of the blocks here. For instance, Pandas has great capabilities of reading different data sources. And numpy and scipy and Pandas, they together can do a lot with data cleaning, data manipulation, and feature engineering, which is what people spend a lot of time on when building machine learning models. And last but not least, in the Python ecosystem, there's also a whole set of machine learning libraries, and the number has been increasing with the rising of deep learning frameworks with TensorFlow and PyTorch and things like that. It just becomes really, really powerful for people to deal with data science. If we look at the same thing with Spark, Spark is actually pretty cool as well. Spark has these 2 core libraries called SQL and Spark ML, and they can also deal with a lot of problems in this workflow. And on top of that, Spark is also great at dealing with large-scale amounts of data, which Python kind of struggle with. Once you go out of 20 gigabytes of data in a Python process, things kind of starting to falling off. So why don't we just use Spark, right? Spark is great. It's scalable and has all these libraries available to deal with data science. Why not just using Spark? And why is Python still so popular? If we look a little bit deeper, there actually has been a problem, a feature gap. Actually, many of the functions in Python, they are not available or they are not easy to do in Spark. For that, I'm going to show a very simple example of a common problem in data science, especially in data cleaning, called forward fill. The idea is you have a time series of data and some of the values are missing. And one of the simplest things you can do is to carry the past observations in the future if the data is missing. Here is an answer when I type forward fill in Python in Google, and this is the first Stack Overflow answer that pops out. If you look at this answer here, it's not actually super complicated. It's actually pretty elegant as a one-liner with a simple example. And if you're a data scientist, when I look at this, I'm actually quite happy about the answer. I would just go ahead and use it. However, if I type the same answer forward fill in Spark, this is what I got. This is kind of this is also the first Stack Overflow answer that pops out. You don't need to read this, but you get the idea. It's very complicated, and it's definitely too overwhelming for a data scientist. It goes into the details of RDD and data frames, and it's just not great. If we look a little bit closer, the actual answer is actually not that bad comparing to the entire one. It's using a window function in Spark SQL to do the forward fill problem. However, the issue here is because of Spark currently lacks this high-level API and semantics to deal with this problem, people do have to think a lot harder and jump through a lot of hoops to get the final answer, even for someone who is experienced with Spark like me. And this is not only a documentation or a discoverability issue. There's actually a feature gap between Spark SQL and Python in a lot of sense. Using the same example here, sometimes forward fill with the previous observation is just a very basic thing people can do, but sometimes people want to do things a little bit complicated. They might want to take the past field values and do some aggregations on them in order to fill the next one. And if you search for the Pandas documentation, there's a whole page about filling missing values and the functions you can use to do that. And the same functionality does not exist in Spark SQL today, to the best of my knowledge. And if we look a little bit bigger into the picture, there's not just the issue with filling missing values. And these are the actual questions that people have come to me and asked me how to do this in Spark, and I kind of struggle to answer these because those people are so comfortable and familiar with the Python libraries. They just expect to find the same answer in Spark SQL, which does not exist today in a lot of cases. And not to mention the model training libraries, another big set of things that's kind of missing in the feature gap. I'm sure all of you guys have heard Reynolds talk about building new machine learning platforms in Spark, but as of today, these things are kind of difficult to do. So here I want to stop for a second and step back and think about Python and Spark and what they are great at what they're doing, and how do we make them together. Now, Spark is, as we are seeing, it's very good at dealing with scalable data. And Python, on the other hand, has this very awesome set of functionalities that covers all kinds of corner cases in data science, which is why it's so popular and powerful. And how can we find a box that has the best of the two worlds? How can we have something that's as scalable as Spark and as powerful as Python? Is what I've been thinking. This kind of brings out the problem and motivation behind this feature we created. And next, I'm going to walk you through this new feature in Spark 2.3 and see how it can help to solve some of the problem I've mentioned. If we think a little bit harder about Spark and Python, we can find that they are really great at doing their individual things. So Spark with its Spark SQL with its relational operations, it's very good at specifying how you want to operate your data. For instance, you can say you want to do something for each row, or maybe you want to do some grouping of the data, or maybe a rolling window, or over the entire data. Spark has very good primitives and pretty efficient executions of these relational operations. On the other hand, Python is very good at dealing with local array-like data structure. If you look at the Python ecosystem, almost all the libraries, they all talk the same data structure. Either it's numpy array or Pandas series, which is just the wrapper around a numpy array, or they talk with each other using Pandas data frames. So they're very efficient in dealing with this kind of data structure, and that's what they are very good at. So the thing we've been thinking about is how do we combine how and what? How do we get what they are good at? How can we get what Spark and Python are good at individually and combine them together? I'm sure all of you, if you've used PySpark, you're familiar with this concept of Py Spark UDF. It is an interface for extending Spark with the native Python libraries. Two interesting things two kind of important points I want to mention here is, first, the UDF is executed in a separate Python process, which means it has all the library dependencies and functionalities you can have in your local notebook. And the other thing I want to mention is because of Spark is inherently a JVM-based system, and all data is kept in the JVM, you need to transfer the data into the Python process in order to execute the UDF. And sometimes that process is not as easy as you think. Let's take a look at what the existing UDF can do. It's basically a Python function on each row. For data serialization, the data is serialized from Java to Python back forth using Pickle, which is just a standard Python serialization protocol. And last, the data is presented as Python objects, for instance, Python integers or Python lists. And as I mentioned, these are not really very native Python data structure if you talk about data science. And those objects, they usually have pretty high overhead and poor performance. There are a few issues I want to highlight with the existing UDF. First of all, because of the UDF only operates on each row, you're missing a lot of the powerful features from Spark SQL in terms of relational operations. Second, there's a huge usability issues as well. You don't need to read the code, but the idea here is I'm just doing a simple data normalization group by year and month. The normalization is V minus the mean of V divided by its standard deviation. So it's a pretty simple transformation. However, in order to do this group by transform operation in PySpark UDF, you have to write a lot of code with boilerplate just because it does not support the group by semantics out of the box. And if we look at the code a little bit in highlights, this is the code that actually has meanings in this whole chunk of code. And over 80% of the code is just boilerplate. And those not only cause huge usability issues, and also they cause performance issues as well. Last but not least, I want to talk about performance issues with existing UDF. Here I'm profiling the simplest UDF I can think of, x+1, using the existing UDF. Two things I want to highlight here is first, the overall throughput of doing this operation on a double column is only 8 megabytes a second, which is not great performance by any standard these days. Also, the other thing I want to highlight is that you can actually see over 90% of the time is spent in serialization and deserialization and not actually running the computation itself. With these three issues I highlighted, I think there is a challenge to make the UDF interface better. The first is we need a more expressiveness API to deal with different semantics. And second of all, we need a more efficient execution process. First, to transfer the data between Python and Java more efficiently. And second of all, once the data is in Python, we actually want to execute the operation efficiently in the Python process themselves. With that, I'm going to talk about what is released in the Spark 2.3 release. There's two types of Pandas UDF. The first is called Scalar, and the second is called a group map. So on the very high level, we introduced a new function called Pandas UDF as a new alternative to the existing UDF function. The difference between these two, I'm going to just quickly go through and highlight them. First is, as I mentioned earlier, existing UDF is a function on row, and Pandas UDF can be a function on row, group, or window. And for the serialization part, the existing UDF uses pickle serialization, and the Pandas UDF uses arrow serialization, which is a more efficient binary format. Last but not least, on the data structure side, existing UDF uses Python objects, and Pandas UDF uses more efficient data structures like Pandas series and Pandas data frames. Just a quick overview of what is Apache Arrow. It's going to just to be 2 slides. In one sentence, Apache Arrow is a in-memory columnar format for data analysis. It's designed to have extremely low cost to transfer between systems. When you're converting an arrow table to Pandas table, it's actually almost close to 0 cost. And the idea behind Arrow is we want to create a data format, or a language rather, that can be spoken by different systems. Here I'm showing on the left side, there is the current state, whereas we have this a set of different systems, and whenever they want to talk to each other, someone needs to build a custom converter between their memory representation, and that's why it's preventing them from communicating or reuse each other's component. And on the right side, with the introduction of Arrow, if everyone can all just convert to Arrow format or have a converter from the internal memory presentation to Arrow, then it's much easier to talk with each other. And that's exactly what we did with Spark and Pandas on this graph. Now I'm going to actually introduce these two type of UDF and how you would use it by giving a few examples here. The Scalar UDF is really simple. It has the same semantics as the existing UDF. It's just mapping between one-to-one mapping between rows. The difference is, first, the serialization is changed from pickle to arrow serialization, and also the UDF itself has been changed to a vectorized version. Beforehand, it only takes a single number, and now it takes an array of numbers and also return an array of the same size. I'm going to show two very simple examples here. There's a little bit of a code reading here. Hopefully it's not too much. But this is actually something I found quite interesting, which is converting a millisecond long value to timestamp. This is bring that simple transformation. However, it's not that easy as you think. If you Google it, it's not like a simple solution in Spark today, because Spark uses a second if you just cast between them, and you lose position if you just cat a millisecond to second. And here I'm showing a simple way to do it using the pandas function to datetime. So pandas can do that pretty easily. And if we wrap them using the pandas UDF, then you have the capability in Spark. The second example is this function called CDF in SciPy library, which is to compute the cumulative density function for a number. The details are not important, but the idea is most of the CDF function in SciPy also has a scalar version and a vectorized version. And the vectorized version is actually over 100x faster. So in this case, the speed up is even greater than the timestamp case. And that's all I have to say about a scalar UDF. And group UDF is a little bit complicated, but it's also, well, it kind of makes sense too. The idea of group map UDF is it's an operation on a group of rows. And the UDF operates on each row, and it maps one row to any number of rows and columns. So it's just a very, very high-level map operation. This is similar to flat map groups in Spark SQL, if you're familiar with that, or group by apply in Pandas, if you're familiar with that one. This is actually a very common operation and supported by a lot of tools and languages. This is just a quick illustration of how it works. Here we've broken the process into two steps. The first step is we're doing a group by just using Spark's primitive. So here we're taking full advantage of the Spark's efficient group by operation. And the second step here, for each group, we apply this UDF on the data frame, and we basically go through the Python, the arrow serialization again, apply the UDF, and get the results back to the JVM. In this illustration here, we're just doing a one-to-one mapping, so the output the table still have the same number of rows as the input, but in reality, it doesn't has to be the case. It can be more rows, less rows, anything you want. Here, I'm going to show a quick example of the backfill. We've talked a little bit about this before, and here, by leveraging this backward fill function in Pandas, we can actually wrap it in a UDF and just do it pretty easily. And one thing to note here is because the group by map UDF needs to take the return value of it is an entire data frame, so you need to specify the schema of the output table. Here, because of we're not changing the schema of the input and output, we're just passing the input schema of the data frame. This is a single example I want to show here, which I also think is kind of interesting, but it's a little bit long, so please bear with me. This is an example where I want to group my data into different subsets, and I want to train a model using just a simple linear regression on each subset of the data. Here the code is split into two parts. The first part is I have some code to define the constants. What is my feature? What is my response? And what's the output schema it's going to look like? And the second part of the code is I define the UDF to actually train the model, which is basically just calling the statsmodel.ols.fit method. And finally, I'm just collecting the model parameters, which are the interesting stuff in the model, and send them back to Spark. This example is actually quite interesting because one use case we've seen in time series analysis in particular is if you have a long time series, you want to train models on it, you kind of want to see the predict power over different time periods. And this is a very useful tool to do that. You can define a time-based grouping scheme, and you can kind of observe the effects over time of the data. And in the UDF, you can also do some model testing. You can kind of return maybe a model score from the UDF instead of the parameter. There's a lot of things you can do with it. So that's all I have to say about these two features. If you're interested, definitely reach out. with me later, or there's a Jira ticket about this. I'm very happy to answer anything, or if you have any usability issues. But here, I do want to show the improvements and the limitations of this new feature. First of all, we talked about usability before, and here's the code to do the same data normalization using the existing UDF and Pandas UDF. And we can see there's definitely a pretty big usability improvement. The code is much cleaner and easier to read. There's also this performance improvement, which is covered by, which was also shown in the blog post here. The idea is we can get a performance improvement anywhere from 3x for a simple +1 UDF to over 100x if we're doing something like a CDF function, for instance, using SciPy. And I have to say, I mean, Pandas UDF is really great, and I really like it. However, it has limitations that you must keep in mind. The first limitation is because the nature of the idea, you must split the data. So if you want to run a Python function across the entire Spark data frame, there's not really anything you can do with it. You just have to collect everything into Python and do with it. With the UDF function, you have to split the data in some way. Also, another limitation with the group map is because we are invoking the UDF on the entire group must be able to fit in memory. So this could become an issue if you have very large groups or you have highly skewed data, which also cause very large groups, in which case you must think about how you group by the data more carefully to be able to fit in memory. Lastly, I want to talk a little bit about ongoing work. There's not much slide, but I think it's quite exciting to me to keep doing this work. This is the roadmap for the Pandas UDF in the next few months, I think. This is on the top is the Jira ticket. It's the master Jira to cover all this work. So if you're interested, definitely vote this Jira, comment on the Jira, anything. I will be very happy to answer on the Jira. Also, here we cover what's released in Spark 2.3, and there's some exciting work. For instance, we have already implemented group by aggregate UDF, which is just degeneralize the case of group maps. You only return one row from your grouping function, so that's an aggregate. This work has already been merged, but not released yet. Also, there's a working in progress for the window UDF, which is a slightly complicated problem than the group by, but also I think we are making pretty good progress on that. So hopefully you can have it in your hands soon. Also on the other side, we are dealing with some of the memory inefficiency currently, especially on the JVM side. We are looking forward to improve that, which is ongoing work as well. And finally, we are looking forward to provide the complete type support. Currently, the Pandas UDF can only work with primitive types like string, integers, and array types. We really want to deliver the struct type and map type to you. I think those types are very powerful in machine learning and training models, so you can return pretty flexible data from your UDF without having to specify very complicated schema. With that, I will conclude my talk. And again, thanks for joining me, and I'm happy to answer any questions. Thank you.